What's up, everybody? Day 156. 56. So, two goals for today. We're going to look at opaque and transparent. Hopefully, two words you've heard of, but if you haven't, well, now you have, and we're going to define those today. Also, we're going to think about why it is that things appear different colors, why they're bright, why they're dim. Some good stuff. We're going to be covering color and light as part of our electricity and magnetism waves, or electromagnetic waves, I should say. Chunk of the waves unit. And it's all some very applicable stuff to understanding why it is that you see things the way that you do. So, exciting things to me. Pretty cool when I learned them. Let's go through the warm-up. We've got thinking about the word void, and then a little bit of review. Some folks are still struggling with echo questions. So, if you haven't started these already, go ahead and do them now. Did you do them yet? What about now? Okay. Void. Lots of meanings for the word void. For something to be void of something, it just means that it's empty. Space, right? Space is, it's not quite empty. There's stuff out there, but it's pretty empty. There are particles out in space, but they are few and far between. Search and rescue worker needs to know the depth of a cave so they can choose the correct length of rope. So which speed should they choose? E&M waves, which would be the speed of light, or the speed of sound? Well, how are you going to make an echo? How are you going to figure out how deep the cave is? You're going to make an echo. Two ways to make an echo. One would be to yell and wait for the sound to come back up. The other would be to shine a light and wait for the reflection to come back to you. Which of those things do you think you could time? Definitely can't time the reflection of the light. Even if there was a puddle down there, you're going to turn the light on, and it's going to feel like that light comes back to you in the exact same instant that you turned it on. You can hear the switch go click, and the light is going to shine back up in your eyes from the puddle down at the bottom of the cave. So that wouldn't work. You'd have to use the speed of sound. So you might go boop, and then at 1.2 seconds later you hear boop. And so, knowing that, if you want to find the depth of the cave, well, depth is it's a distance, right? So if we want to find a distance, what equation do we use if we know time and speed? It's not even a wave equation. It's the first equation we learned or reviewed in class this year. Speed is equal to the distance divided by the time. S equals d over t. We also learned velocity is displacement divided by time. In this case, since it's a straight line down and then back up for the sound, either version works. So we don't know the distance, so we need to solve for that, which means we need to have distance on the top, and we're going to move the time to the other side of the equal sign. So we're going to have speed multiplied by time equals distance. That means we have to multiply 1.2 by 343. And that's going to be the answer. Let's see. 1 times 343 is 343. 0.2 times 343 is 68.6. So 343 plus 68. Oh, man. 343 is 403 plus 8, 411.6. I hope that's right. Let's find out. Woo! Yes! I can do multiplication. Okay, so that would be the answer. We'd have to write it in 2 sig figs, so it'd be 410 meters. And I don't know if by you, but if I was the rescue worker, I would round up. Also, a 410 meter rope. That's 4 football fields worth of rope. Maybe a lot of rope. I don't know if ropes come that long. I don't think so. If you're a rock climber, you probably know. I used to be a rock climber, but I was 13. It was a long time ago. I know. I look young. Okay, so moving on. E&M waves and transparent and opaque. A little bit of notes and some practice questions. So, opaque. If something is opaque, what does that mean? If something is transparent, what does that mean? So if something is opaque, then I'm trying to think of things that are opaque. Sometimes people in their house have windows in their bathroom that are frosted, so you can get some light through, but not all the light. And the light that does come through gets bent and blurred, so you can't see anybody's private bits. Um, so that's an example of opaque, smoked glass, um, things that reflect and refract some of the light. All right, so they bounce back. That's reflect, and refract is to bend some of the light, but not all of it. All right, they let some of it come through. That's opaque. Transparent things are things that allow frequencies to pass right on through. So we've got those two differences there, and you want to write down some definitions for those in your notes. Now, water, is it transparent? I've got some water here. All right, and if I take this and if I took some of this water and, where is it? Here it is. If I pour it out, you can still see through it. I can see the bottom in there. Looks transparent. Is it transparent? What do you think? I need a haircut. What do you think? Is water transparent? Let's look at this picture. I got a picture, a cool picture of water. I got this from a dive photo guide. Take a look at this picture. This is a nice photo of the ocean and a shark. I would not do this. No. X. You know that little emoji with the X? That's me and swimming with sharks. No thanks. But what do you notice? What's missing from this photo? Something is missing. Okay. What color is missing? Or colors? What colors do you not see? There's definitely some colors that are probably there, but we can't see them. See what's missing? Do you see blue? Okay. Green? Not really. Red? Orange? Let's go through the colors in order. Remember, it's Roy G. Biv. So, red would be first. Do you see any red? No. Oi. That's orange. Do you see any orange? No. What about yellow? I can't tell if this is yellow down here or what. Maybe. G would be green. Again, I don't know how much green there is in this part of the ocean, but I don't see any. Biv. Blue. Do you see blue? Well, yes. Indigo and violet, that'd be kind of like purpley tones, and I think those are present. So it seems like mostly just blue, indigo, and violet are here. If we scroll down a little bit on this link, you'll see that, oh, look at this. Water is 800 times denser than air, and this density absorbs light. And what it actually does is it starts to reflect it or refract it. It bends it. Refract it starts to bend it because the density is different, and different media, different materials, traveling from one media to another is what causes light to bend. So we see this picture here. Some light gets reflected, and some is going to get refracted, which means it's going to get bent down. And we can see that we lose the red light within 5 meters of depth. We lose the orange within 10, yellow within 20, green at 30. And then blue, we lose blue at 60 meters. It's really deep, by the way. It's 180 feet. And this is why it gets dark. All right, if water was purely transparent, you would be able to swim to the bottom of the ocean, and it would be just as bright as on the surface. But we all know that it's not. All right, that's not how it works. One, there's particulates in the water. There's little bits of food, algae, poop, just all this dead stuff, right? And there's all kinds of things that are naturally there. I'm not talking about the plastic and stuff that we put there, but there are all these things that are there. And so some of those things block and absorb light, but also just the fact that water is a different medium. All right, that's key. Causes refraction, causes the light to bend. This actually has something to do with why you see that right up there in the color that you do. Right? You only see it like that in the daytime, right? It doesn't look like that at night. It's something to do with light. Okay, so cool fun fact. So there's a little bit of reading about light and frequency and the order of color in terms of wavelength, and that's all on Schoology. And so let's just take a quick peek at what that looks like. Here it is. There's a little bit of reading on the physics classroom. Do 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 do. So just looking at electromagnetic waves and visible spectra. That's the visible spectra is the visible part of the wave spectrum, or the part of the wave spectrum that you can see. Remember, the visible part is just this teeny little slice of the wave spectrum. It's just this little part right here that I'm showing you. There's all these other waves. And so one of your assignments is to draw this, try to memorize Roy-G-Biv, think about why it is that when a light shines through a prism, we got white light coming from the sun, why when that goes through a prism you get this rainbow. You may not have a prism at home, but if you have windows where they have some kind of beveled edge, where the edge is kind of angled a little bit, it'll bend the light, and you'll get rainbows when the sun shines through. So there used to be a little activity right here where it says investigate, but it disappeared. I don't know what happened. Anyway, there's some check your understanding questions right here that are good ones to think about, and I also put those on the handout, which is here. And this is a quick little 15-minute activity, just going over some basics. Yes. Okay, cool. So, and then leading into tomorrow, we're going to start talking about color, color interaction. This is how we're going to mainly understand the electromagnetic waves. Is how colors interact and how we perceive the visible light spectrum. Because then you can apply that to everything else. So you've got a reading assignment on color. I've uploaded a full chapter for the color chapter from my favorite conceptual physics book, and I think it's loading right now. Seems to be stuck. Okay, got everything to load. So this is your guided reading, and this is, to me, this is really interesting because, for all of us, we see. So how is it that these little things work, right? So, like today, I'm repping UC Davis. Congrats, Francis. Got into UC Davis. Whoop, whoop. Go Ags. My shirt's blue. Why? I mean, the light coming from the sun is white, right? How come my shirt's not white? Well, so my shirt's blue. Why is it blue? Why is this grass green? Why is my phone red? So, all these questions, right? Today's reading answers all these things. You're going to look at the spectrum. Remember, we talked about spectrum, what that is, the span. Excuse me. So, thinking about when you shine light on something, why it appears the color that it does. And then also, if you've ever done this before, maybe you've used a headlamp and it just has a red light for a night light, or maybe you've had some party lights in your house where they just shine one color, like just red or just blue. You ever notice that some things that are one color, they all of a sudden they're not that color anymore? Like things that were red, if you shine a blue light on them, they're not red anymore. They're not even a dull red. They're black. Why? So this reading goes in to start to answer that. And we're going to spend the rest of this week and next week doing some explorations with filters and different colors of light to examine why that happens. If you have like a red soda bottle or a red piece of film or a blue bottle or a blue piece of film, right? I'm talking about like a blue soda bottle that's plastic. If you have any of those, keep them around. And if you don't have one and you see one, grab it and just cut a little square out, like this, and you can use that to do some experiments at home and use it as a filter. It's pretty cool. We'll talk more about that later on. Okay, so a little bit of reading. The reading is pretty good. It talks about doing things like splitting up white light. Is white a color? Why do things look black? The edge of a razor blade, really small, right? Is it black? The rest of the razor is silver. Why does the edge of the razor blade look black? It's still the same razor, right? What's that about? Question 11. What if something absorbed all light? Where does brightness come from? Are different colors brighter than others? And, like this kind of question. What kind of street light would be best so that you see the most at night? All right, this would be good if you were a city planner. This is a real question. So, some cool questions there about color to start considering as we continue to explore light. And that's it. So it's a beautiful sunny day. There's lots of white light everywhere. It's reflecting off everything. And let some of this light from the screen reflect off your eyes and do some exploring. And I will see you all tomorrow.